Okay, I hope. Okay, it's finally unmuted. Yeah, so there has been. Yeah, so there has been many attempts to generalize the notion of gram of hyperbolicity. Like the body just come up with a relative hyperbolicity, and there's also the Morse boundary and the sublinearity Morse boundary. He visits a, he visits he visits basically a collection of geodesic rays from which quasi-geodesic segments with endpoints on them he are either bounded distance apart or a sublinear distance apart, and like this is a new. I mean new. I mean not ex- Yeah, 2024 is new. Yeah, so this is the new, and this is one of these new generalizations which is well defined for a broader class of metric spaces, and invariant under it's invariant under quasi isometry. So that's good because it just cares about the large scale geometry, and if it's chromophypobolic, then it is the chromo boundary. Here are some definitions, and alpha and beta are quasi-geodesic rays, and we say that alpha redirects to beta if for every r greater than 0, you can find a QQ quasi-geodesic ray. This QQ is fixed for all r. Such that it coincides with alpha inside the ball centered at alpha 0 of radius r, and it eventually coincides with beta, and we say that alpha is equivalent to beta if alpha redirects to beta and beta he redirects to alpha, and like these are some assumptions that we make to ensure that it's well behaved, and here's how the boundary is defined. Okay, so right now, yeah, okay, so right now, this is the uniformitization theorem, which is that a simply connected, a simply connected Riemannian surface is conformally equivalent to either the sphere R2 with a Euclidean metric or the hyperbolic plane, and Gregorian has shown that conformally equivalent to the hyperbolic plane, that a surface is conformally equivalent to the hyperbolic plane. A simply connected surface is conformally equivalent to hyperbolic plane if and only if Brownian motion of M is transient. Okay, I'm stating it here because I'll be using it later on. And this bounded geometry is basically we are assuming that the sectional curvature and injectivity radius at all points are bounded, and the sectional curvatures and the injectivity radius at all points are bounded, then we can come up with a quasi-isometric triangulation of the Riemannian manifold, and if M is closed, then we can also say something stronger, that by making the triangulations arbitrarily fine, we can find. We can get a sequence of triangulations such that it with the path metric with suitable rescalings, it converges to the closed manifold and in the Gromov-Hausdorff convergence. So I'm just stating it that because once you get this triangulation, you can make MG quasi-isometric to a rotationally symmetric plane, which is And of course, this F is smooth. And we know that if R it's, you can think of the rotationally symmetric planes as as rotating this curve around this around the z-axis, and the resulting surface that you get, it's basically that. And basically that, and basically that, and then you get at both of them. It can be triangulated with the same graph which is quasi-isometric. It do both and it do both and due to a result from Kaimono, which I should have cited, we get that they have the same conformal type. That is to say, both of them are either conformally equivalent to the Euclidean plane or to the hyperbolic plane. Okay, this bounded geometry assumption is very important because you can have an F such that in addition to that, infinity, and for such an F you get that it is, this is just for ensuring that the Brownian motion on this plane is tangent, so that it is conformally equivalent to the hyperbolic plane. So then if we disregard the assumption of bounded the bounded curvature and injected radius, then we can get a conformally hyperbolic plane whose quasi-redirecting bound is just a point. And here's the proof. Conformally equivalent to R2 even. Yeah, this is for the case when it's conformally equivalent to R2, and if it's not conformally equivalent to R2, I think I should use this. I think I should clarify what spleniate is. So then you can make it. So then you get a triangulation, and then you can make it quasi-isometric to a carton, a carton hammered a manifold such that you, I mean you, such that you get at the limit, it, that the limit of, yeah, that is, the limit exists and it lies and it's strictly greater than zero and less than infinity, and we are interested in cartan Heidemann manifolds because they have no focal points and therefore have the very neat property that that all geodesic balls in them are that all geodesic balls in them are convex. So the shortest path, the path joining any 2 points on the boundary of this ball, that does not intersect with the interior. It's precisely this arc which we get from the convexity, and from it we get a geodesic rays do not redirect to each other, and therefore we get at this holds that the boundary is S1. Now here's how the Martin boundary is defined, and here's how the Martin boundary is defined, and here we are assuming that the Brownian motion on M is transient, which is equivalent to it admitting a Green's function because he'll be and if it's recurrent, then if M is complete and non-compact, then you identify all sequences going off to infinity with each other, so you get a 1-point compactification, and if it's compact, then there are no sequences going off to infinity, so the Martin boundary is empty, and it's just that. So here's how the Martin boundary is defined. Actually, I should have stated this part in the stated in that quasi-geodesic rays converge to a unique point in the geodesic boundary if it's conformably equivalent to H2, because then it ensures that redirection is symmetric, and like the redirection is symmetric, and this part also ensures that all quasi-geodesic rays also converge to the Martin boundary, and like this is a decision, and like this follows from the fact that geodesic rays do not redirect to each other, because otherwise if it did, then if it has multiple limit points, say then that it interact to each other, and okay, here I should have mentioned that that the uniqueness of asymptotic cones is very much dependent on the continuum hypothesis holding because because Mark and Sapir because Duda and Sapir showed that for higher rank semi-simple Lie groups, that for higher rank semi-simple Lie groups, that if the CH is that if the continuum hypothesis is true, then it has the unique asymptotic cone, and okay, but however, it is true that if any of its asymptotic cones is an artery, which is okay, the next slides are that if it's an artery, then it will be Gromov hyphen. Artery is basically that, and the artery in question that we get from it being an asymptotic cone is, it's basically an infinite graph where each vertex has degree. The C where C is the cardinality of R. So here are the references.
All right, so questions? Yeah, hi. So in the case of, let's say, a symmetric space, like to be concrete, SLNC mod SUN,
Yeah.
what do these, what is the Martin boundary and quasi-redirecting boundary look like?
The Martin boundary, will always be, will always be a, for irreducible symmetric spaces, it will always be a sphere, but if it has a rank greater than or equal to 2, then it will, the quasi-redirecting boundary will just be a point. While for rank 1, it's Gromov hyperbolic, so it will again be a sphere which coincides with the Martin boundary.
And also at the end, you mentioned these R trees. Have you thought about R buildings? The generalization to R buildings?
Yeah, these are the asymptotic cones of the higher rank symmetric spaces, and
More questions? No? Okay, let's thank Ritvik.